Hello, welcome to a new food4Rhino webinar. Good evening from Barcelona, and welcome Rick Barua and Dr. Neil Goldie Kumar from Intact.Simulation. Today, Dr. Neil Goldie Kumar is going to show us the new topology optimization included in Intact simulations for Rhino Grasshopper. And Dr. Neil Goldie Kumar is a product manager at Intact, and he has a PhD in mechanical engineering, and he leads the development team at Intact Simulation. We are really eager to see this new addition, and yeah, because well, today Intact Simulation is the greatest topology optimization and FEA plugin for Rhino and Grasshopper. This webinar is being recorded. Later today or tomorrow, it will be added to our food4Rhino YouTube playlist. So in case you miss a part of it, don't worry, you will be able to watch it later. And remember also that there is a chat panel that you can use during the webinar. You can post your questions there, and maybe Rick can answer this on the fly. Otherwise, at the end of the webinar, during the last 15-20 minutes, I will pass your questions to Neil. So, Rick, Neil, many thanks for being here today with us. And yeah, we are ready to see what you want to show us.
Cool. Thanks, Carlos. Thanks for the welcome and hosting us for food4Rhino webinar. Hi, everyone. Great to see all of you here. So today we are going to dive into LevelOpt, our new optimization engine that builds on Intact.Simulation, our meshless Intact simulation, which we introduced almost 2 years ago. And today we'll show you how you can go from not just simulating your part, but evolving into a much better design, more optimized design, but all within Grasshopper, the environment you already know and like and love. So without any delay, let's just jump into it. So many of you already know us. We are Intact. We have been around for a while, almost 25 years, mostly doing research, but last 2 years ago, we made a splash bringing our next generation simulation technology, especially starting with Grasshopper in Rhino. Since then, we have also introduced our integration within NTOP and Synera, more computational design tools. And then now we also have our automation product we call PyIntact. So if you're a designer who uses multiple tools, all sort of working together to aid into your design, and you want simulation in your workflow, then Python API or command line interface can sort of help you there. So all of this is our third generation technology now, very robust, and we have built over the years. So we started in Grasshopper with Intact.Simulation. Just a quick overview of what that is. So with Intact.Simulation, we brought in industrial strength FEA within Grasshopper, leveraging all the flexibility and the automation and reusability that Grasshopper provides. But when you bring simulation, the traditional mesh-based simulation, some of these workflows break because meshing, as you know, if you know, is a huge bottleneck in these traditional finite element methods. So our simulation, which doesn't rely on these conformal meshes, but on non-conformal meshes, basically removes all these bottlenecks and then allows you to fully integrate simulation in your design workflows. This is a simple example of a workflow we did of a shoe design. Basically, just a quick overview. On the left side, you see pressure data coming directly from experiments with individual users and different stances of their walk. All of that pressure data comes in, streams in, gets converted into boundary conditions that gets applied in finite element in our FEA. Then you have multiple simulations at different stages of walking automatically done based on those pressure loads. All of these results are combined now, which can tell you where it sees more stress and where it sees less stress. And based on that, you can now design a more optimal, more performant shoe sole for your customer. In this example, we were doing some fancy design with lattices. We put more material in the lattice by thickening the walls. in the gyroid where there was more stress, and then less thickness where there's less stress. So just to give an overview of how simulation basically is in the background, giving you the right feedback at the right time to make better design decisions. So that was Intact.Simulation. It has been out for almost 2 years now. We have seen a lot of success out there already, a lot of cool usage. Shout out to Moonrabbit Adaptive Lab for this use case, where Jesus designed and his team designed this, again, high performance shoe, but not just aesthetic in mind, but performance as well. And on the right, you see a helmet design, again, lightweight, comfortable, but meets the functional requirements that was imposed on. Some more examples, again, Spherine. These are very high performance but complex lattices, which are adaptive density minimal surfaces. Can be really hard to mesh these geometries, and if you wanted to optimize the lattices for your function, it can be really challenging in traditional FEA and traditional workflows. But then with Intact, meshing is not a bottleneck, so these and analyzing such structures is very easy. And last but not least, the last example is Slice Lab, where they were designing high performance thigh pads. And as you can see, these are strut-based lattices designed to absorb impact. So again, a lot of parameters to pick from, different types of lattices, thicknesses, sizes, and how do you decide which one is the best one, or at least good for your use case? So you need to have simulation in the backend to tell you that, to give you that feedback. So a lot of cool use cases we have seen over the years. But that brings me to LevelOpt, which is basically taking all that power we have behind Intact.Simulation and using that in the core for a new topology optimization based on level sets, and we'll see more on that. So what is LevelOpt? So it is a level set based topology optimization, which has, as I said, Intact's mesh-free FEA technology in the backend, which makes it really powerful. As you can see in the image here, it gives you very smooth manufacturable shapes. Unlike traditional topology optimization like SIMP method, density-based methods, there's no patchy, small, weird features, no voxel artifacts, very clean design, ready to be used right after optimization. And not only that, the FEA validation is in the loop itself. So the simulation that generates all the sensitivities is through Intact, not some heuristics FEA, so very accurate FEA. And the design that comes out is fully validated already. We have a lot of advanced features. It works with assemblies. You can decide which regions to preserve, which regions you don't want to preserve, and design, remove material from. It supports both isotropic and orthotropic materials. And we provide you the full flexibility through parametric control that you expect in Grasshopper. So really let designers fine tune the design the way they want to. So at this point, I will quickly go into a live demo. So this is just a bracket, I think one of the NASA Excite brackets. And we wanted to show you how LevelOpt works, what are its features, powers, and some of the differentiations compared to existing optimization out there. So now I'll jump into Rhino. I'll minimize this right now. So familiar grounds, Rhino, we have the part in different layers here. So just to give an overview of the problem, so we have this as the design domain where we want to remove the material from and design this optimized bracket, but then it's attached to this component here, which sees a load on the back face. So we have boundary conditions. As you can see, the back face has loads on it. And then we have some fixed restraints on these rings here. So it's an assembly optimization, but we want to optimize only this piece of it. So I'll turn this off for now and go directly into Grasshopper. Oh, sorry. All right. All right, so we are in Grasshopper now. Uh, just to show you how Intact simulation looks like within Grasshopper. Once you have Intact installer, you install it. Just like any other plugin, it will show up in the ribbon up here, Intact.Simulation. Quickly, we have all these blocks that allow you to do simulations and optimizations and visualization. So for simulation, we have modal vibration simulation, stress solver, thermal solver. Optimization right now is mostly for compliance or minimizing compliance. So we use the stress solver. Next, we have support for components and assemblies and different types of materials, both isotropic and orthotropic. We have standard set of materials you can plug in, or you can bring in your own materials, custom materials as well. One of the powers of meshless simulation is that it doesn't only work on traditional B-reps, so your poly surfaces and meshes and whatnot, but we also work with implicits, level sets in a volume format. So you can read these implicit volumes and simulate them as components within Intact as well. We'll come back to LevelOpt in a bit, but we have all the boundary conditions you need for stress solvers, thermal solvers. I have some of my custom blocks. You can always make custom blocks in Rhino, Grasshopper. And then finally, we have the visualization tools to look at your results, read results, old results, and also sample results in regions you want, and then use downstream to drive your decision. So anyway, this was the plugin, but we are here for LevelOpt. Two new blocks if you have the LevelOpt now. One is the optimization block itself and a new settings block for that. All right, so let's see how a typical optimization workflow looks like with LevelOpt. So first, as we said, it's built on Intact.Simulation. So we have to set up a stress solver, a stress simulation, and that will be the input to the optimization itself. I won't set up the stress right now. It's preset. I'll just walk through it quickly, but then we will see in detail how the optimization looks like. So in this case, we have the stress block. It takes in components, the components you want to analyze. So we have two components, as you can see here. The design space is this one, and the non-design space is the block you see in the back. You have the restrained surfaces where it will be fixed, and then we have load faces where we apply some loads. Again, we have several loads, but this one uses vector load, as you can see right here. Very straightforward. No messing around with anything else. Just feed in the basic input to stress. And we have very high level solver settings, which essentially tells the stress solver what's the fidelity of the simulation. Do you want a coarse simulation? Do you want a fine simulation? So you can control the cell size or the number of elements you want in your simulation. But there's no monkeying around with meshes and remeshing and all that. So it's very straightforward. So once all of that is done, you just run the stress simulation. I'll rerun this. It's very quick. As you can see right here, the logs is almost 100,000 elements in the simulation, and it solves within seconds. Almost done. Yeah, it's done. And this is now results on the original geometry. So this is how the stresses look like. Von Mises stress, as you can see, and then we have a range of quantities you can visualize. So what's the total displacement? What's the strain, max principal strain, and all that typical FEA quantities you want to see. So that was your Intact simulation, the traditional, the workflow we already had, but now you want to bring in LevelOpt. All right, so we have I have some inputs here already, but let's bring in LevelOpt. So this is the block. It has a lot of inputs here. So we'll go over one by one. Let's leave the settings for the last. So first is, what is the component you want to optimize? So this is the design component, which is directly pulled from the design space. So that's the design component. So we'll feed that in. So it has the geometry and material. Next is give us the stress scenario. What are the boundary conditions? What does the stress look like? So we feed that in. This is stress simulation directly. Then how many iterations do you want? So let's say we have 20 iterations for this one. And then what's the volume fraction? So this is asking how much weight reduction do you want? So we only want zero point 0.2, meaning 20% of the weight. So remove 80% of the weight, and it will try to do that. Some more input, we don't go into there, but you can see the LevelOpt block is actually ready to run. All the settings can be left to default. But since we are in a live demo, let's try to make it a little quicker. So I will add LevelOpt advanced settings. And this move limit is just telling it to move the boundary faster. So one is the default setting, but two will move the boundary faster to converge faster. So I'll plug that in and I'll bring that in as advanced setting. And while we run this simulation, I will explain all the other settings, which gives you this very fine control on the design, but which we'll see when this optimization is running. All right, so with this, we have all the input we need for our optimization. We just go ahead and hit run. And now it'll be running Intact in the background, computing sensitivities, changing design, and all that. So it takes a little bit of time. Meanwhile, we can look into what these advanced settings are. So we have a very robust manual documentation of the LevelOpt optimization. So you can go through here, but I'll just focus on the settings just to show you how you can really use the settings to fine tune the design you want, not just get some default black box design. So first one is the level set cell size. So this basically tells you how fine features you want in your design. 0.25 is a fraction of the size of the simulation cells. The smaller the fraction is, the finer details you get in your design. So I think the example here would be, you can see right here, when you have cell size 1, you get this design. But if you reduce the cell size of the level set, you get more finer features. So you can control that. Next is move limit, which I actually used right now. So if you want to make design changes quickly and you're not worried about refinement yet, you can have a higher move limit. You can see it within 10 iterations, it reached here versus a smaller move limit. Your boundaries are moving slowly, the level set boundaries, and your refinement is more precise but slow. So that's what move limit does. We have smoothing iterations, so you can smooth the design, get rid of any weird artifacts every couple of iterations. By default, it does every iteration. We have fixed thickness. This is essentially telling the optimizer to preserve some of the functional regions, so where loads and boundary conditions are being applied. You don't want to remove material from there. In your case, then you can specify a thickness of how much material you want to preserve. So you can see 4 preserves this much red region, but 10 will preserve a larger region where your forces and displacements were applied. So that's what fixed thickness does. Then we have retain interfaces. So in your assemblies, where the two components interact, you can ask the optimizer to preserve that interface completely or start optimizing that interface as well if the entire interface is not needed, for example. So that's what that setting does. Our optimization is done, actually. So let's go back here, and we'll come back to rest of the settings in a bit. So optimization is done. You can see it did 20 iterations. Let's look at the results now. So basically, the optimizer outputs all the design iterations, and you can go look at them one by one. So I will just use a block to, not panel, item, list item. Yeah. So we have a list of design iterations, and we want to look at the designs one by one. There are 20 iterations, so I'll create a slider from 1 to 20. Okay, and let's look at the designs now. And this is how the design evolved over different iterations. As you can see, it's removing material while trying to maximize stiffness. And this is the final design we got after 20 iterations. Very good already, looking nice and smooth. If you wanted to look at how more details on how the iteration happened, you can look at the volume fractions and the compliance values at every iteration. All that data is available. So that's how easy it is and how quick it is. Within a few minutes, we have a very good design optimized to as a source of inspiration for how to design this part, or you can start refining this design itself if you wanted optimized design like this. So that's the first piece. So we are able to optimize this, but just to push this further, how easy it is to take this and then fully validate right here instead of exporting it into as a CAD and bringing in some other FEA. I'll show you both power of Intact and Grasshopper workflows right here, right away. So we want to now analyze this geometry and what the stresses and displacements look like. And we already have the solver set up. We already have this set up right here. The only thing that changed is now we have a new design, but rest of the boundary conditions, the loads are the same. So I'll just copy those, paste it, and I'll bring it over here, right? So everything remains the same, except we saw that the design changed. So I will just input that. Sorry, it's a little small here. Yeah. So we're now just feeding in the new design, but rest of it as we saw before, it remains the same. So we have the new design. Let's leave the cell size at 2, but let's say you want to do finer refinement, finer simulation, you can always reduce this. And it's ready to go. So you run this new simulation now. Again, very fast. And we have results available. So now you want to look at the stress, for example. And right here, we have the results. You can see now the stresses are higher this time in several regions. The material is getting used more optimally. You can validate that. You can start looking at deflections and other quantities and see if your new design meets the criteria or not. So that's how you have design and validation right in this same workflow right here. Let's take this one step further. So, okay, we were able to reduce the mass by 80%, but I want to go further, make it further lightweight, but I want to do it in a more refined manner, meaning more finer features, more thinner walls I want. So that's also possible with LevelOpt with one of a very key feature here. Let's see, which is starting geometry. So essentially, you can chain together multiple optimization and start from a new baseline and not the original. Your design domain can be the original design, but you can always have a guess of where to start. So this time, for example, we can start from where it ended last time. So we can just feed in that as the starting geometry. Rest of the inputs look same, so we want to optimize the same design domain. Uh, we have the same stress simulation. It's already here. I will still want 20 iterations, but this time I want to reduce the volume mass by almost 95%. So it'll go from 80% to 95% reduction. But I want finer features. So that's where some of these advanced settings come into play. So now I can have a very fine level set, almost 1/5 of the size of the cell, and this will give us even thinner features. And I can put that in here. And it's done. And let's run the simulation. So you'll see how it takes the 80% design, optimized design to 95% now. It will take a few minutes. Meanwhile, I can maybe show you a few other things you can do. So, oh, lost it. Yeah. As I was saying earlier, that these designs are very nice and smooth, and it's very easy to essentially export as a step file, thanks to LevelOpt and Intact's smooth design simulation. So let's say I have this first design saved here. This is what it looks like in its mesh form. Um, you can, for example, use Rhino's quad remesh capability. You can select that design, enter, and here I want to maybe smoother design with almost just 200 meshes, but converting into a subdivision surface. And you provide all the inputs and you just export it. And I'll just show you what the end results look like. So this is the kind of sorry, what else happening here? Yeah. This is the kind of geometry you can get out of LevelOpt right away. Not a lot of cleanup, post-processing needed. The design is already very nice and clean and smooth, and you can just use Rhino's built-in quad remeshing and subdivision surfaces to get a nice surface patch STL out. This is one example. Uh, Still going on. We are almost done. 18 iterations. I'll turn this off. Right. All right. So it looks like the second optimization is done now. So this is the refinement optimization. And again, we started with the 80% design and then pushed it further to 95% reduction. And let's look at what the final design looks like. So we have all the list of designs right here, as you can see. And we want to again walk through these designs one by one. So I'll create a slider, select this. And you can see how that 80% design is now further being refined and creating thinner and thinner features. As you can see right here, these small features and these walls have become very thin now, thanks to this 1/5 of the level set cell size of the simulation cell size. And you can keep playing this with these settings further and get the kind of design you want. And not just that, like I used an existing optimization results to further refine it, but you can bring in your own constraints, your own cutouts, and your own aesthetics to the design, and then use that as the inspiration for optimization for the next step, essentially. What is it? Yeah. Okay. So that was how we can chain together optimization to build these complex workflows, as we saw. So we took the original design, did an 80% reduction of the weight. Then finally, we further refined it to 95% reduction. And you saw the validation was built in, and then exporting that design was no pain at all. So that was the demo for LevelOpt. Next, I will just quickly show you more examples of the type of designs you can do in different application areas. So the first one is in the AEC area. Here you can lightweight structures driven by form driven by function. So for example, this is a pedestrian bridge design through optimization, where you have this design domain in gray. The blue is the actual bridge where the load will act, and the red regions are where you want the supports to be. And then basically you just let LevelOpt work, and you can get these very clean designs optimized. Either you can, most likely use this as an inspiration and then go from there and refine it based on how you want to make it. Other examples of how to use LevelOpt. This is a splint, mass customization. So how do you make a lightweight brace, for example? And we made this example, but let's say to showcase that you had some features you wanted to preserve in the splint, like these rings and some connections between them, and then optimized from there. So you would apply some loads on that, and then you just let the level opt work, and it'll find the optimal ways to connect these, make these connections. Again, other application will be a drone chassis design. You want it lightweight but stiff. This is an example of that. So 80% reduction, as you can see. I talked about that we can do both orthotropic material and isotropic material. So isotropic material is the first one. I think this is aluminum. This is kind of the design you will get for this bracket when you do isotropic optimization. But then if you were to do orthotropic material, I think this is carbon epoxy with Kevlar fibers. You get a very different kind of design. The load paths have changed. You can reduce, uh, so your designs can change significantly. So we have ability to do directional material as well. All right. But anyway, so that was all how traditional optimization work, like in a black box, but we still showed you how you can break this into smaller iterations and get more control in the loop itself, breaking into more coarse set and then refining or injecting your design choices as the optimization is happening. But this all can be taken to one step further, and I don't have a live demo for this. This is more involved, but I just wanted to give you a quick example of how through LevelOpt we give power to the designer by allowing them to have user-guided optimization, right? So because we know that optimization typically gives you these blobs, and sometimes you don't want that, and you want to intentionally change your design in a certain manner through certain parameterization uh, for various constraints you might have. So I will exit out of here to show you that first, what that looks like and how to do that. So typically, you know, what we showed earlier was just the black box optimization, but this output I did not go over earlier, but this is design sensitivity. So basically, we are outputting also how sensitive your design is. Let me bring in a visualization here in certain areas. So this is telling the velocity on the surface of the level set. It's telling you where if you remove material, it will reduce the stiffness, but but the other areas where you can remove material safely. So the red is sort of no go, don't remove material here, huge impact to stiffness, but the blue is you can easily remove material here. And this is an output we provide you on the surface mesh, and you can take this output feedback and then basically drive your own parameterization, own optimization engine, own optimization rule, for example, and not just let LevelOpt change the design automatically based on this feedback. So that's something you can do with LevelOpt. So the example here was showing how one way to use this. For example, this is a casing housing where I don't want to get a blob at the end of the day, but I wanted to remove material in these pre-specified cutout regions, these orange regions, and it's just in the one corner, but it's in all four corners, the same thing. And but I don't want to remove material in these cutouts just uniformly, just making this cutout same depth everywhere. I want to control the depth of this cutout based on where it makes more impact in terms of keeping the stiffness, least impact to the stiffness, for example. So I don't want optimization. You just run LevelOpt with one iteration. It doesn't change the design, but it'll output the velocity feedback, which you see here. So we made the cutout domain as the design domain, and rest of it was part of the assembly. So now you see this velocity feedback on the cutout regions. And the more red is telling you not to remove material, and the blues and the greens are telling you you can remove material. But you can see it's a very organic, smoothly varying field. But I don't want to remove material organically. I want to make cutouts, uniform cutouts for each profile. So you can look at the velocity field and figure out which ones have more significance for the stiffness, so the red regions. So you want to have very minimal cutout there, but the green ones you can cut out more freely. And that's what it's telling. Oh, I don't know why it's doing that. Yeah. Okay. And that's what the next slide, the result shows you. So you can do this in multiple iterations uh, in within Grasshopper, and through 5 iterations, we are able to get to this design where you can saw it removed again in a uniform manner, but more deeper cuts in these areas and shallower cuts in these areas. But this could be, for example, for a machining or other constraints where you don't want blobby, non-uniform depth. And this is the results. Again, you just plug it back into Intact and you get the results. You see the 15% weight reduction with only 7% decrease in max displacement, increase in max displacement. So this is an example of what LevelOpt can do once if you really want to take charge of the design optimization itself and how the design from iteration to iteration will change. I think with that, I'm at the end of our presentation. So Intact.Simulation with LevelOpt is available right now. You can go to intactsolutions.com and try it. Um, we give a very easy way to get to 2 week free trial. And just to recap, it's fully integrated in Grasshopper. So it's fully automated, reusable, parametric. You can use it for both exploring conceptual designs or refining your final design. You can put these LevelOpt, create more complex optimization and design workflows by combining multiple of them, as I showed you with course and refinement. Bring in your own parameterization if you want to. So it supports both black box and user-guided optimization. As you see here, the designs are very smooth, very clean, very CAD friendly. No to minimal post-processing needed. Right now, it's compliance and all the stress boundary conditions are supported, assembly supported, but more physics and constraints will be coming soon. So that's LevelOpt. Very powerful. And at this point, I think I'm ready to take questions.
Wow, what a great demo. Many thanks.
Yeah, thank you.
It's incredible. Um, yeah, there are a few questions. Rick has been answering this already, but maybe we
Yeah,
can
yeah.
go
So
through them again
we
or
can, yeah, I can help facilitate that. I think Carlos, some of the questions they wasn't able to get to all of them. So let's start with Mano's question. Mano asked a while ago, the quad remesh plus sub D conversion does not retain the exact input mesh shape. So will the sub D still conform to the load requirements?
Um, I don't
I'm
know
not
what
sure. Yeah, I'm
yeah,
not sure. I understand that question.
yeah. So we use Rhino's sub D. If you have any other better ways to get to the step file, that works too. But that's the easiest one, and seems for in our experience seem to be very um, high fidelity to the mesh. Um, right. So
Right. And then there were some questions about nonlinear physics. You can address that with the group.
right. So right now we have stress and we have thermal and other optimizations, but non-linear will be further down the road for optimization. Yeah.
And also for our simulation too, right? That's not we're not supporting
Non-linear yet.
Yeah,
Yes.
large deformation, nonlinear at this time, but that is on
Right.
our roadmap.
Roadmap. Yes.
Going through these questions. There's a question for Miroslav. There can be several different materials within one set: metal, plastic, wood.
Right. Yes. Very straightforward. In right here, you can always just create a new material and plug that in into the other component. And yeah, it can be whatever, plastics, engineering plastics. Yeah. It's very straightforward, or mixed composites and isotropic material.
Right. And Rhino Grasshopper allows that flexibility, right? We can add and then say an assembly of multi-material kind of components in there.
Right. So multi-material, we support bonded assemblies, and you can see you don't have to pre-specify where the contact is. We just infer the contact from basically they have to be close to each other, and based on the cell size, if they're close within first certain threshold, it will automatically get bonded in the simulation. Yeah.
Julian has asked, is it possible to add material in stressed regions with a positive volume fraction constraint, maybe? That's kind of like your starting design uh, thing that you
Right.
showed, right?
Right. So yeah, if you go with a starting design and let's say your design domain is larger, but you removed your starting design, removed material where it was needed, and you allowed the design domain to be large enough to add material. So it will add material in that region as well. Yeah.
Okay, got another question. Is it possible to optimize structures made of lattices? In your opinion, to what extent can AI assist LevelOpt? Great question.
Yeah. So, AI with machine learning, with just generating data with Intact directly right there, you can leverage. You saw how fast simulation is. So if you wanted to generate hundreds and thousands of data points, very straightforward. These are high quality data points. We have sensitivity information. You can leverage that. We have some internal stuff going on, which we can't discuss right now, but yeah, very friendly for machine learning type design algorithms. What was the first part of the question?
Can it support lattices, the
Right,
optimization?
right. So the if you just use the black box, it will it will just try to remove the boundaries based on the sensitivities. So if it was a gyroid, you might end up with something else. But if you wanted to optimize preserving the parameters, then you may have to look at just the velocity and then decide, come up with a way to update the lattice parameters if you wanted to preserve the lattice type. Yeah.
Ite has asked an excellent question. What is the technology behind the solver? Is it MFEM or based on other technology?
Yeah, I didn't go much into the technology itself, but at a high level, I had a backup slide. It's a meshless simulation, but it's not voxel density, all that heuristic. But basically, we immerse the grid, the geometry into a regular grid of it's coarse here, but these grids are very fine in practice. And then it's regular FEA in the sense the inside cells are just regular element, hex elements, and the boundary cells are where we do a lot of custom integration based on what order, what accuracy you want. And then we project the solution. We solve on the blue grid and then project the solutions on the original geometry. And this allows us to be fully in the background, automated. You don't have to fiddle with meshes, convert your native geometry into a volume mesh, for example. Yeah. So that's the
Right,
technology. And
right,
level up takes it to the next level. Yeah, essentially. Yeah.
right. And also, I would add, so the solvers, those are homegrown. Like we have developed those solvers that we're using,
Right.
but we can link up with really any solver, including MFEMs and even Nastran. We have some prototypes, early prototypes that we
Right.
use Nastran as the solver to make it mesh free as
Yeah.
well. Because in the background, as Neil said, this is it's a traditional FEA technology. We're just, instead of meshing the geometry itself, we're meshing the space around it. And
Right.
if you want additional information, we have published papers on IMM. You can send us an email and we can be happy to walk you through them.
Right.
Is there more information about the verification of the model and validation of the model for applications?
As in benchmarking the simulation itself, or
Right. Menno, if you can help us kind of understand that better. But yes, we have benchmarked against standard FEA problems and provided by NAFEMS, and benchmark against other commercially available software as well. And typically we see in displacements within 1 to 3% and stresses around 5% or less in a fraction of the time.
right.
More expense.
And then yeah, we can provide the benchmarking documentation if interested.
If nonlinear is on your roadmap, can you indicate when that would be available?
I would say not this year, next year,
Not
most
this
likely.
year, right,
Yeah,
right. So
yeah,
this
yeah,
year,
yeah,
you can expect from us more expanding our linear capabilities, including more assembly level like context and such. And then next year, 26, probably we're looking at bringing some more nonlinear capabilities in to our solvers.
right,
And I think we mentioned this in the past as we've been around for 25 years. We have developed a lot of technology, and so far we've only deployed maybe 10% of it. But we are a small team, right? So that it takes a little bit of time for us to kind of make sure that we're providing the right tools for our customers. So, and we get this question quite a bit. When is nonlinear coming? Because that could be very game changing. So
right.
that is coming. How do we define the right grid size?
Right. For simulation, usually you can define the cell size based on the features you want to capture. So if there are holes and bending members, and you want certain number of cells through those to make sure that the behavior is captured accurately. So you directly describe the cell size. But so that's how you do that. And for LevelOpt, you decide the cell size of the level up the level set basically to based on what kind of features you want in your design. So as you saw, we went with a default size here of 0.5 of 2, this cell size. So there was 1 millimeter, but then we went further down when we refined the design to 1/5 of the 2, so basically 0.25 or sorry, 0.4 inches, millimeters.
So he's
So
asking for, do you have any recommendations? So I think it's really depends on the model, right? Depends on the
right,
geometry, the
right,
size of the geometry.
yeah. And if you don't know it, you know, in FEA, you just have to do a convergence study. So you keep changing the resolution or the cell size, decrease it slowly. And when you see that your displacements are leveling off, flattening, that means you have reached a convergence. So if you don't know, otherwise, if you know exactly how many elements you want in what regions, then you just directly pick the cell size. Yeah.
Right, right. And for Intact simulation, we recommend going with the resolution instead when you run your first simulation, right? And our logs will kind of tell you like what cell size, you know, it was used for getting to that resolution. So that's
Right.
a useful
Right.
thing.
Yeah.
Okay, can you explain what training materials is available for our product?
Yes. So we have, as you saw, it just popped up for some reason. Yeah. So we have documentation for LevelOpt right here with some examples. We have if everything is set up, you can just download it and start playing. And then our Intact.Simulation documentation lives here, uh, doing it live. Yeah. So you can go and look at Grasshopper. Basically, we have a lot of documentation videos on how to basically set up basic simulation, what the steps look like. Yeah, so we have all this first getting started, and then also some of the advanced examples where you want to do composites, reuse, do VDB, volume components, sampling custom points. So all of these are available. And if you need any help, we're always willing to quickly help you out as well.
Right. Also, if you follow us on LinkedIn, we post workflows and videos quite often
Right.
for Rhino Grasshopper and our other products as well. But anytime we show a workflow, we always we can send you that workflow that we create, right? So it's an easy way to get started, get going, because we want to make sure that, hey, I mean, this FEA stuff can be kind of new and for designers, right? Even I came from a designing background, so it took some time to learn and all that, but with all the tools and knowledge that's available through our wiki here, it's very helpful and easy to learn and pick up.
Right. Yeah. And
And
you
our
can
software
see,
is very easy to use. That's
yes.
the best part.
Yeah. Yeah. And we gave as many, sample documents for you to get started, look at the workflows, so you don't have to create everything from scratch.
Right.
Yeah.
All right. Another question. Do our solvers use GPU behind the scenes?
No. And mostly because we haven't seen the need for it yet. Because you
Yeah.
saw like 100,000 elements, degrees of freedom within a matter of 10 seconds. We run 10 million, millions in, I would say, 15 minutes. So we haven't really seen a huge need for GPUs yet, but if you were if you saw the need and wanted to scale further, we will definitely as we said, it's very easy to hook up other solvers, so hooking up a GPU solver will not be a problem. Yeah.
Right. And then our solver is multi-threaded. It uses all processing power you have. And Neil was running this a live demo on a web presentation. It still took only 10 seconds to run the simulation. That's pretty amazing. So
Right.
kudos.
Yeah. Yeah. So it's fully parallelized, you're right. So you
Yeah.
use all the cores on your computer. Yeah.
Yep. I think I captured all the questions. If I missed one, I apologize. You can probably type it again.
Yeah, I think you covered them. Many thanks.
Okay.
Yeah.
Yes.
No, no, great.
Very good
Also
questions. Very
because you
good
understand
questions.
the questions better than me, Sometimes
Yeah.
I can read the
Yes.
question, but I don't know if I don't know the plugin very
Yeah.
well. I don't
Right.
understand the.
Yeah.
So Rick
But
and
but
Neil,
but, but yeah, real quick. So you can get a free trial of our software, right? Free trial of LevelOpt, free trial of Intact.Simulation. Just go to our website. I think I posted a while ago in the chat. Post it here again. And then you can start a free trial. And our pricing is also on our website. It's very transparent. You can buy from our website if you like the product. And again, we're always happy to answer questions and help along the way.
Right. Right here.
great. Many, many thanks. It was very inspiring and very powerful. And yeah, also thanks to all the participants that make these webinars feasible. And as said in the beginning of the webinar, at the beginning, I will upload the recorded session to our food4Rhino YouTube playlist in a few hours. So you will be able to watch it again. See you next in CD Farm, New York, not in Amsterdam, but New York or earlier. Yeah, whenever you have a new version or new features in Intact.Simulation or LevelOpt, please let me know because we will be very happy to share this with the Rhino Grasshopper community.
Thank you,
100%.
Carlos.
Yep.
Yeah.
Thank you. Thank you for your
Thank you,
time.
everyone, and have a nice day and a nice evening. Bye.
Bye.
Bye.